So very happy this afternoon to have some talks on low dimensional topology. First talk now, then there will be a break, some refreshments upstairs for those not on Zoom, and then talk at 4. So first speaker is Slava Krushkal, Corks for exotic diffeomorphisms.
Thanks very much. I was worried about not being able to say all the words in my talk and draw all the pictures, so I got some computer talk. And so let me, oh, is this a little bit bad? This doesn't quite fit. That's okay. So I'd like to give just a very brief and quick survey of different notions of mapping class groups of all the four manifolds are going to be simple connected in this talk. Sorry, university, given all the disclaimers. So classification of homeomorphisms. So this is in the topological category. This is a theorem of Frank Quinn about 40 years ago that this is determined by the action of homeomorphisms on the second homology of the four manifolds that preserve the intersection pairing. So the mapping class group is just automorphisms of H2 with intersection preserving the intersection pairing. And well, I should say that one can't quite say that this is entirely due to Frank. There's a huge amount of work in the background. Of course, anything about topological four manifold builds on the theorem of Mike, about the disk embedding theorem. And there was some corrections of Gauguin and Heidegger in 90, and then more recently, last year, there was a correction of one of the key steps in the proof, also in the paper with Dave Gabay, Dave Gay, Daniel Hartman, and Mark Powell. And there's also other related work. There's work of Craig in 79, which I'm going to mention in a little bit, which essentially classifies diffeomorphisms up to pseudoisotopy, the diffeomorphisms of four manifolds. And then there is a paper of Piran where it seems more restricted, but more or less it does the same thing that as Frank Quinn does for topological pseudoisotopy. So he proves the topological pseudoisotopy theory for four manifolds, theorem for four manifolds. He got some restrictions, but we explain in this paper that actually prove a statement that's equivalent to Frank's for topological four manifolds. So anyway, it's a theorem of Quinn, but there is a lot of work in the background related to it. Okay, but so ultimately, if you have some diffeomorphisms of four manifolds, then this simple connected four manifold is very easy to check that they're topologically isotopic just by checking that what they do on the intersection form. Okay, then there is a notion of a stable smooth isotopy where we can connect with certain number, some number of S2 cross S2s and connect some with identity. And you say that two diffeomorphisms are self-diffeomorphisms are stably, smoothly isotopic if they become isotopic after it connects some with a certain number of S2 cross S2s. And the statement I'm going to use is that if you have a smooth four manifold and two diffeomorphisms are topologically isotopic, then there is stably smoothly isotopic. And one way to see this is using work of Frank that was corrected by us, and the independent proof is due to Gabay 2 years ago, where he does not trivialize a given pseudoisotopy, but he just shows that, anyway, his proof is different from Quinn's, and the conclusion is also not as strong, but this statement has two independent proofs. Okay, and then let me, without explaining what they are, just mention some examples of exotic diffeomorphisms. The first examples were given by Ruberman in 98 and then 99. And there has been quite a bit of work over the last few years. There's the Dane twist on K3 connects on K3 due to Kronheimer-Mrówka in 2020. And then there are some more examples of Oracle Econo, Jonathan Lin, and others. So I'm going to return to some of these examples at the end. Okay, so here's our first theorem that if you have a compact, smooth, simply connected Frome manifold and a self-diffeomorphism, which becomes smoothly isotopic to the identity after a single stabilization with S2 cross S2, and you can assume you can take your manifold to become connected, closed. If it's not closed, then it's the identity on the boundary. If it's compact and not closed, then the conclusion is that there exists a smooth, contractible, codimension 0 compact submanifold, so that the diffeomorphism is isotopic to one that's supported on this submanifold, an identity on the complement. And so we call this a diff cork for the diffeomorphism. So again, if it's a self-diffeomorphism that becomes isotopic to the identity after writing a single copy of S2 cross S2, then the conclusion is it's actually isotopic, it's supported in the contractible submanifold. So most of my talk is going to be about giving an outline of the proof of this. And the second theorem is when you have an arbitrary number of S2 cross S2s. So suppose you have a simple connected Frome manifold and a diffeomorphism, which is topologically isotopic to identity. So by a theorem that I mentioned a couple of slides ago, that means that it's stably smoothly isotopic to the identity, but we don't know how many S2 cross S2s you need. Then we can show that it's supported on this codimension 0 submanifold. We cannot prove that it's contractible. We can find a submanifold which is homotopy equivalent to measure 2 spheres, so that the inclusion is null homotopic in the Frome manifold, so that F is supported on this, up to isotopy is supported in this submanifold. And I'll give an outline of this theorem as well. And so let me just review some background and also like where all this comes from. So there was some earlier work due to Agbalut and Kirby on first examples of corks, Frome manifolds where you start with a smooth Frome manifold. For some specific contractible Frome manifolds, you can cut them out and reglue it with a twist using a different diffeomorphism and produce exotic smooth structures this way. And it turned out that this is always the case, and that's proved by in these 2 papers in '95 that whenever you have 2 two smooth structures in a Frome manifold, then you can always construct an H-cobordism, smooth H-cobordism relating them. And then the theorem for H-cobordism, the cork theorem for H-cobordism is that you can find a contractible sub H-cobordism so that it's a product in the complement. And when people talk about corks, they usually assume various other conditions. So for example, you can actually show this two C0 and C1 are diffeomorphic, not real boundaries, so that the 2 manifolds, 2 Frome manifolds at the top and the bottom are just obtained by cutting out and regluing this contractible submanifold. But and there is an involution on the boundary in particular. But in our case, it's kind of not really a natural assumption, and we don't really have an involution. So So we use the word cork in the sense of just a contractible, compact, smooth, codimension zero submanifold, so that your structure is kind of supported on this submanifold. Okay, so anyway, so this is kind of the background for our talk, and in our case, we're going to go through pseudoisotopy, which is one parameter family of diffeomorphisms. So in a sense, this is kind of using the same methods as we're using these theorems in some kind of related construction in the setting of pseudoisotopy. So let me say a few words about pseudoisotopy. So we work with four manifolds, and in high dimensions, this theory was developed by Cerf and then Hatcher-Wagner and corrected by Gusa and others. So Cerf is so Cerf did a simply connected case, and Hatcher-Wagner developed the abstraction theory for non-simply connected high-dimensional manifolds. High-dimensional means dimension 6 and higher. As far as I know, dimension 5, there is not unknown. I think there was some work of Gusa, but it's not published, and I don't think that it exists in literature. And for four manifolds also is. Anyway, let me say a few words about abstraction theory, and then I'll make a comment about four-dimensional case. So pseudoisotopy is, if you have an isotopy, then it's a one-parameter family of diffeomorphisms, and it's a diffeomorphism of a four-manifold cross an interval to itself, which is level preserving. Okay, pseudoisotopy is a diffeomorphism that does not have to be level preserving. So it's a diffeomorphism of four-manifold cross an interval to itself, and it restricts to the identity on the bottom and on the boundary across the interval. Okay, and the cool kind of game in this theory is if you start with something like this, the question is, can you isotope this diffeomorphism to an isotopy so it's level preserving? So for example, if you have two diffeomorphisms of a four-manifold, then Craig classified them up to pseudoisotopy, so frequently can construct a pseudoisotopy just like this. And then if you could show that it's actually isotopic to an isotopy, then in particular it shows that your two diffeomorphisms are isotopic. So this is kind of how one uses pseudoisotopy theory. So this is a result of Craig in '79. So in particular, it follows from his work that if you have two topologically isotopic diffeomorphisms, then they're smoothly pseudoisotopic. So our assumption is always that you have two diffeomorphisms that are topologically isotopic, so we move on to a pseudoisotopy relating them and try to see what we can extract from this. Okay, and so the way that one studies pseudoisotopy, going back to Cerf, is using the Cerf graphic. And so one starts with two Morse functions. So this is a picture of x plus I, where x is a dot, and I is that, this is I direction. And so there are two Morse functions. One is just the projection. So if you start with x plus I, you just project onto I. And so this is kind of the entry, there are no critical points. So here, this is the projection onto the second factor. And for this one, first you apply the pseudoisotopy, the diffeomorphism from x cross I to x cross I, and then you project onto the second factor. So this is projection 2 composed of F. And then, well, then you can kind of interpolate them between them using, they aren't necessarily going to be Morse functions, but they are generalized Morse functions that have third order singularities. And so one draws a Cerf graphic that I'll also be drawing in this talk with some isolated degenerate critical points in this family. Okay, and so looks at the serve graphic, there are no critical points at the left and the right. So there's kind of just a picture. The actual serve graphic is in the middle. If you could cancel all these critical points, then you'll construct an isotopy and show that your two diffeomorphisms were actually isotopic. Okay, so just a few comments about the Cauchy-Wagner abstraction theory. We are not going to see any of that because we work with simply connected four manifolds. But so there is a primary abstraction sigma of f, and they show this also works for four manifolds as well, that if this abstraction is trivial, then you can deform your one parameter family of Morse functions so that you have this picture. This is so this is a one parameter. If you look at the vertical slices, except for these particular values, you have this is a one parameter family of h-cobordisms, and these are critical values, critical points of index 2 and 3. So there's a 2 handle and a 3 handle. And I'm sorry, there's somebody in the chat. Should I be checking the chat or not? Okay, all right. So my entire talk is going to be talking about the serve graphic, so I'm going to postpone the discussion now. But to begin with, you can imagine there are all these critical points of all the different indices, 1, 2, 3, 4, and so on, and there are handle slides, and the point of this result of Cauchy-Wagner is that if this abstraction sigma f is 0, then you can actually clean it up and you have this picture. And again, I will explain what happens in this picture later in the talk. Okay, so in our case, this abstraction is trivial, so we can always assume that we have this serve graphic. And there's a secondary abstraction defined on the kernel of the first map sigma, when you assume that you have these nested eyes. And so this is much more elaborate. And I just want to make a comment that for four manifolds, there should be a much more refined abstraction that has not been formulated yet. In the sense that, in higher dimensions, what Cauchy-Wagner and Negusa prove is that if the secondary abstraction also vanishes, then you can actually deform the pseudoisotopy to an isotopy. For four manifolds, we would like to, for good groups, we would like to prove the topological pseudoisotopy theorem, or maybe a stable smooth pseudoisotopy theorem that you can trivialize the pseudoisotopy smoothly up to S2 cross S2s. But it's pretty clear that these abstractions are insufficient and you need some more refined abstractions, but it's not been done yet. But again, for this talk, this is not.
What is chi in the denominator there?
There is some homomorphism from the K3, and so this was, I think this was missed by Cauchy-Wagner, and this is a contribution of Negusa. I will not be able to reconstruct this right now.
I see, but it's some map of the
Of K3, so yes, that's right. Nice. Okay, so just like one studies h-cobordism by looking at the middle level, so if you have a smooth h-cobordism of four manifolds, then you can cancel one handles and four handles, and you have two handles and three handles left, and one looks at the middle level after the two handles are attached, and you see the belt spheres of two handles and the attachment spheres of three handles, and everything is encoded in that picture. So similarly, Quinn's approach in this 1986 paper is analyzing what he called the middle level, which is that dot in the middle of the serve graphic. And so what happens in the serve graphic is that, so first there are no critical points, then TB is the birth times, so several 2-3 handle pairs of worn. So let me draw a little bit. So between TB and TF. F is for finger moves. So this is so I'm just illustrating the picture in the four manifold. So you have a bunch of 2, 3 handle pairs. So this is what we call them A spheres and B spheres. So these are 2 spheres on the middle level of the H cobordism. A spheres are the belt spheres of 2 handles, and B spheres are the attachment spheres of 3 handles. So between TB and TF, you see several of these pairs. All right, and then as the horizontal time progresses at the finger move time, what you see is a bunch of finger moves take place. So, something like this. Right, and so all of this, after the finger move time, everything evolves by anisotropy, and then towards the end, there is a TW, which is a Whitney move time, where all of these double points get resolved using some other Whitney disks. And then there's a death time. So between these two, again, you have some standard picture. So what I drew here is actually the time over here after the finger move time. Okay, then after the Whitney move time, you get the standard pairs and then they die. Okay, there is nothing here. So this is kind of the summary of what happens during this in the serve graphic. And so what Quinn summarizes in the middle level is.
Sorry, Slava, can I ask?
Yes.
In the last slide, are there any handle slides like a B1 over B2?
So there are no handle slides. So once the first primary abstraction of Catril-Wagner vanishes, there are no handle slides. You can assume that there are no handle slides. So what we call the Quinn core, actually, let me just draw a separate picture. I think this is roughly what it is, but in general, so the Quinn core is going to be for Q for Quinn. This is going to be the collection of all the A spheres, union the collection of all the B spheres, and this is all you would need for H cobordism. But since we have a 1-parameter family, we also keep track of. These are all the finger move disks. And these are Whitney disks. And so what happens in the middle level is that this is a particular four manifold. So you look at the middle level, which is just a dot in the serve graphic, which represents the four manifold. In this four manifold, I'm just drawing a single pair AB of these 2 spheres, A and B, and 2 collections of Whitney disks. One of them we call the finger move disks, the other Whitney disks. And what happens is that as you start from this middle point, when you move to the right, the Whitney disks are used to resolve all the double points. And as you move to the left, the finger move disks are used to resolve all the double points. And in general, there's a lot of complexity in how the finger disks intersect the Whitney disks. So if, for example, in this situation, if V and W were disjoint, then you could actually trivialize this particular pseudoisotopy and just get rid of all the critical points. But in general, V and W intersect, and you can very easily come up with some examples. You can start with this family like this, and then very easily construct some examples where it's not clear how to trivialize just by introducing intersections between V and W. But in principle, this handle body, which is the neighborhood of this 2 complex in the middle level, determines the entire pseudoisotopy. So it's A, B, and the 2 collections of Whitney disks for all the double points, for the additional double points. Okay, so in general, when you have a picture like that, would be a huge mess because you have many pairs. Even for a single pair, there could be multiple additional pairs of double points, and V and W could have different, so there are different ways to pair them up. Use the Whitney arcs. The Whitney arcs for V and W could intersect on the A and B. And in general, if you take the union of Whitney arcs on A and on B, there will be an immersed arc and a bunch of immersed circles. So the picture on the left is supposed to show Whitney, a situation where the union of Whitney arcs is an arc, because you can see there's an arc on A and there's another arc. So there's an arc for W and an arc for V, and the union of them is an arc. What the picture on the right is supposed to show is that you could have a different pairing of these intersection points using the finger and Whitney disks, where in this picture the Whitney arcs are parallel, and in that case V union W forms a two-sphere. There's a little bit of origin in A and B, but V union W union origin, a bigone in A and a bigone in B forms a two-sphere. But in general, it's some mixture of these, and you could have, sorry, I think I have some picture later in the talk. You could have more general polygons that don't have to be bigons, and there will be a lot of intersections between V and W and intersections of boundary arcs also. Okay, and so what Quinn showed on his paper is that you can actually, for a single pair of A and B, you can actually deform the whole family. He developed this whole calculus of moves on these finger and Whitney disks, so that there are no circles, and there's just this, one arc on A and an arc on B, and the arcs are embedded. So it's the picture on the left, but in general, you could have more of these double points. So something like this. This would be W1, W2. This would be D1, D2. So some picture like that. So we're going to use this condition in our cork theorem. Okay, so this is I'm just restating our theorem. So if our theorem is that if F admits a surf family with a single I, then we can find a contractible cork where the diffeomorphism is supported. And what we use is, this is a statement in Gabai's paper 2 years ago, that if you have a diffeomorphism that's stably isotopic, smoothly isotopic to the identity, stably, then the number of S2 cross S2s you need corresponds to the number of i's in the pseudo-isotopy of F. Okay, so a priori, these are two different things. You could have a surf graphic, you could draw a surf graphic for F, and there's a certain number of i's. And separately, we know that a diffeomorphism that's pseudo-isotopic to the identity is stably isotopic to the identity, but the number of S2 cross S2s you need is precisely the number of i's that are needed in this pseudo-isotopy. So the first theorem I stated that we prove is for a single S2 cross S2s, S2 cross S2, and because of this result of Gabai, we can just work with a surf graphic with a single I. This is the point of this slide. So from now on, I'll just work with a pseudo-isotopy with a single I. Okay, so this is our picture. We have two spheres, A and B, and we have this Queen's arc condition so that the finger and Whitney disks are lined up like this, and you can compute that up to homotopy, this Queen core A union B union B and W has two spheres, which are A and B, and then a bunch of circles that correspond to the intersections between V and W. Okay, but it's crucial for us to have this Queen arc condition. Otherwise, there'll be additional second homotopy coming from those two spheres which have been formed by V and W. Okay, and then this is an ingredient that is taken from the 95 papers on the corks for H cobordisms. once you have this situation that you have a codimension 0 submanifold sitting in your manifold at the middle level, which has free fundamental group, which is given by those circle weight factors, summons, you can complete it to a handle structure of the entire manifold. Well, first you add a bunch of one handles that creates a bigger pre-fundamental group. And then there's a little bit of group theory that shows that you can find two handles that precisely cancel all the free generators of Y1. But we're trying to find something contractible, so it's very important for us not to create any more homology or homotopy groups. And so it's important to only attach two handles that precisely cancel the generators of the fundamental group. And you can do that by some elementary manipulations of these handles in this handle structure of the relative handle structure of the complement. Okay, so we attach these two handles and it makes this queen core simply connected once you attach the two handles. And then all you have left is S2 wedge S2, which are the two spheres, the belt sphere and the attachment sphere. And then you attach the three handles going up and down. Well, one is a two handle turned upside down, the other is a three handle, and you get a contractible H cobordism, and so that's the proof. So this is the end of the proof of the Cork theorem for the single I or diffeomorphisms that become stable isotopic after a single copy of S2 cross S2. Okay, so I'd like to say a few words about the second theorem when you have an arbitrary number of S2 cross S2s. So you have an arbitrary number of these I's in the pseudoisotopy. Okay, so one comment here is that, so our conclusion is that we cannot find contractible quarks in general, so we find these codimension 0 submanifolds that are homotopy equivalent to a wedge of two spheres that are null homotopic. And it's worth noting that Batni-Gabai's barbell diffeomorphisms are actually supported on essentially up to homotopy of wedge of two spheres that are null homotopic. So they construct interesting diffeomorphisms in the presence of fundamental group. In our case, it's simply connected. You can still study barbell diffeomorphisms, but anyway, this potentially could be an indication that maybe you expect some two spheres there, but we don't know if you can find a contractible quark in general or not. Okay, so I apologize, I mislabeled. This on the right should be B1, and I switched the indices of B1 and B2. Sorry about this, should be B1 and the other one should be B2. So if you have more than one I, you cannot possibly implement the arc condition. The arc condition of Quinn, by definition, you need an odd number of intersections between two spheres to have an arc condition. And if you have different pairs, AB pairs, like in this picture, then what you have are some two spheres that you create by taking the union of V, W, and some regions in the spheres A and B. So like in this picture, you can see there are two intersection points between A and B. So you necessarily have a two sphere. It might or might not be null homotopic because if you have some second homotopy groups in your four manifold, then this two sphere might be essential. And so what we show is that you can actually get rid of all these essential Phi2 elements. Okay, it's actually sort of an interesting comment that this point never comes up in the high-dimensional proof of the pseudoisotopy theorem or in the four-dimensional topological proof, because the way that the proof usually goes is that you consider one eye at a time. So you work with the innermost eye, and the whole strategy of the proof is you just get rid of that eye, and once you erase that, that makes the next eye more complicated. But you never have to consider two different eyes simultaneously. So you kind of work at one eye at a time, and once you simplify one eye, then get rid of all the finger Whitney moves. You can just get rid of it and then move on to the next eye. We can't do that because we're trying to construct a quark that has all the complexity of the pseudoisotopy at the same time. So we're kind of forced to look at the union of all these things. It's entirely too complex.
Well, but could you instead say if you had K nested eyes, say that there were K different contractible corks and the diffeomorphism could be made to the identity by isotopies in these K regions? A composition of isotopies, each one supported in a quark.
I think that this, let's see, so I think that this is one diffeomorphism that has all this complexity in it. I don't think that you can decouple it into different diffeomorphisms. We do have a statement about different diffeomorphisms that you can actually, for a single.
But I was wondering if you could remove the inner eye by a diffeomorphism supported in a cork.
Yes.
And then you're left
by isotopies. I'm sorry,
just
compose it with a diffeomorphism.
Right.
Okay, well, it's a good point. I'll think about this. Thanks. Okay. So this is sort of an example of slightly more complicated example where you have four intersection points, and then you could have a pairing like this, W1, W2, and then a different pairing, V1, V2. And what you see is a two-sphere, which is the union of four Whitney disks that look like this kind of belt on the equator. And then there is a quadrilateral in A and a quadrilateral in B. And so that there's always a two-sphere. There's some choice actually of which quadrilateral to consider in a A and a B, and the difference is measured by two of these additional hyperbolic pairs, but anyway, this is some details. Okay, and so the first step is just like in the single eye case where we add two handles to make it simply connected. So that works because of homotopy type of the queen core is still going to be a bunch of two spheres and a bunch of circles. So we can kill the circles by adding two handles, just like in the previous case. So after that, you have a bunch of two spheres. Some of them are A, some of them are B, and some of them are formed by this finger and Whitney disks. Okay, and so now the strategy is to introduce trivial pseudoisotopies, realizing particular pi2 elements, and then merge them and then get rid of the pi2 elements. So, so what's shown here is that this is the given pseudoisotopy on the left, and we create these additional pseudoisotopies where they're trivial, so they could be deformed away to nothing, but they realize a particular pi2 element, any pi2 element you want. And then you can merge pseudoisotopies together, just prevent this from dying, so it just merges into birth like this. And then once you do this, you can kind of recombine the arcs and the Whitney disks using Quinn called this the sum square move, where you can, if you have two different Whitney disks, you can merge them together, recombine them, and using that you can kill pi2 elements because we created them precisely to cancel the elements. So the outcome of this is that you still have these two spheres, but they're now homotopic and they're four-manifold. So this is kind of there's a lot of detail, but this is the summary of the proof. Okay, just to mention some examples. These are the first examples of Danny Ruberman. So the four manifolds are of this type, and really there are some elliptic surfaces and some log transforms, but after you connect some with some CP2 bars, they all become diffeomorphic, and this is what he used. And I'm sorry, I should have removed the slide. Sorry, this is not a Z infinity subgroup. I'm sorry, Danny corrected me. There's a infinitely generated subgroup that abelianizes to Z infinity. Sorry about this, is incorrect. So this is what he constructed. So these diffeomorphisms can be shown to be one stably isotopic to the identity, meaning that if you add a single copy of S2 cross S2, then they become actually isotopic. And on some level, this can be understood as in terms of the spheres in these four manifolds. The way that he constructs the diffeomorphisms is using some two spheres with framing plus or minus one, and some sort of a complex conjugation in the CP2 that we get, or CP2 bar. And so these spheres are not isotopic to begin with, but after you add an S2 cross S2, they actually become isotopic. And since the use in this contractible diffeomorphisms, the diffeomorphisms are isotopic as well. So anyway, these are examples that meet diff quarks that we use in our. This was kind of the conclusion of our theorem. And Ruberman's original proof used Donaldson's theory, and then there is more recent versions of these diffeomorphisms and uses Zyber-Quidden invariance. And so one corollary of this is that you can construct these diff quarks, the compact, contractible, smooth manifolds, and diffeomorphisms that identity on the boundary that have the family Zyber-Quidden invariant not equal to 0. Okay, there are different versions of this family Zyber-Quidden invariance, and I'm not an expert on that, but I think there have been some other constructions using different versions of family Zyber-Quidden invariance. But more or less, the idea is that there is a glue-in formula due to Jianfeng Ling, and we know for these examples of Ruberman and other examples that the family Zyber-Quidden invariant is non-zero, and we have this contractible four manifold, and we have the pairing formula. So since the full invariant on the closed manifold is non-zero, then it must be non-zero for the contractible piece as well. And another application is, okay, I apologize, it doesn't fit on the screen. So there is a, if you have, so this is a question that makes sense in any dimension. And suppose you have a, okay, since it doesn't fit, let me just write it over here. So suppose you have W is a contractible manifold. Then you can just consider a disk in the interior W. And if you have a diffeomorphism of the disk trail boundary, then you can extend it by the identity on the complement to the diffeomorphism of W rail boundary. And so there's a recent work of Galatius and Randall Williams from us here that shows that this map, which I just described, is actually a homotopy equivalence on the diffeomorphisms of the disk real boundary and to diffeomorphisms of W real boundary. And the consequence, one consequence of our work is that this is not a homotopy equivalence for dimension 4. And this is proved sort of roughly along the same lines as this, using this glue-in formula. But I gave this talk a few weeks ago, and then I heard from Danny Ruberman and Bakuto also has been in touch with us that apparently it's a folklore theorem, although it doesn't exist in literature. Apparently experts know, I'm certainly not an expert, but experts do know that apparently that if you have a diffeomorphism that's detected by some kind of family aggregate invariant, then it cannot be localized on a four-ball. And anyway, this is, we just kind of given a proof that's suitable to our context, which is contractible for manifolds. And I think you guys are writing a different version of this, right? Okay. Okay, so another theorem that was related to what Mike was asking is that if you have several diffeomorphisms that are, if you have a sort of a diff cork, which is a contractible compact four manifold, and several diffeomorphisms that fix the boundary, then we can combine the support into a contractible manifold. And using that and using Ruberman's examples, we can construct examples that generate a subgroup that abelionizes to z to the m. So it's not just a pair of exotic diffeomorphisms, but you can actually have any rank you want. Okay, maybe some examples. So we don't know if you can find a contractible cork in general, if you have more than one eye. Got to think about what Mike said. So for the Dane twist on K3, connects on K3 of Krankheimer and Morovka, it's a theorem of Jan Van Lin that it continues being exotic after a single S2 cross S2 is added. So that means that our theorem does not apply. So we don't know if this can be supported on a contractible submanifold. So this seems like a very interesting question. So absolutely nothing is known about non-simply connected four manifolds, and the version of Piron and Quinn's theorem is not known for good groups, for example, for Z. So you have to use some kind of Cauchy-Wagner theory in a non-simply connected case. And it seems very clear that you have to develop some kind of refinement of Cauchy-Wagner invariance, so that none of that has been done. But there are these results, for example, of Badney and Gabay on diffeomorphisms of S1 cross S3, and it will be very interesting to give a topological analog of what they do. So that some of those are also not topologically isotopic to the identity either. So, but it would be nice to have some actual theorem classifying the non-simply connected case, homeomorphism, non-simply connected case, but that has not been done. And I think that this is probably work in progress. Since I don't know anything about, sorry, I shouldn't say that. I'm not an expert on Floeric homology, but just a comment about this is that historically, the way that corks have been, corks with non-trivial involutions on the boundary have been discovered is that there were exotic smooth structures on closed promanifolds. And if you find a cork, then you know that the involution does not extend to the cork because you can distinguish the closed manifolds using Donaldson or Zyber-Quitten invariance. More recently, technology has been developed to just look to these corks and make no reference to the closed manifold. So there are these involutive Floeric homologies where you can look at this cork with an involution and detect, you have a Floeric homology, you have this four manifold that uses something on the Floeric homology of the boundary, and you can study them using this new tools. And so in principle, you could close them up and start constructing exotic structures on closed four manifolds. So it would be nice to have something like that also in the theory that we're discussing. We deduce the fact that some diffeomorphisms are not isotopic to the identity for this contractible four manifolds because it's true for the closed up manifolds. But in principle, it would be great to have to go the other way, just start with a cork and just work with that. And I think I'm done. Thanks.
Slava, are there questions on Zoom? Put them in the chat or raise your hand and speak.
Well, maybe I should just make a comment. I remember Mike reading your paper about this course from '95, and I think you made a comment that your theorem could have been discovered 30 years earlier. So in principle, this, I think the developments in Feynman's algorithm invariance are new. This is quite new, but the actual theorem, the main theorem I talked about this diff corks, would have been proved right after Quinn's paper because of our condition. So that's like 40 years ago. So, so I can make the same comment about our work.
Is it possible that you could choose the diff cork once and for all for a manifold, rather than look at the particular diffeomorphism?
Well, isn't there also some big questions about the corks like that also just for exotic structure? I think that's no, right?
Yes, I was wondering in the diff case.
Yeah, I don't see a way that it will be easier than the usual cork case. We just, we look at this data in the middle level, and then we kind of add more stuff to it to make it simply connected. And it's kind of difficult to imagine that universal. I think it's conjectured to be not true, right? But yeah. Sorry, I don't know.
Ask a general question. So there's a map from these smooth isotopy classes of diffeomorphisms to automorphisms of the intersection form. What's known about that map?
Well, I mean, I think essentially this is, the automorphisms of the intersection form are the same as the topological, right?
Exactly.
So we're essentially just studying the kernel of it. And
It's always on to.
It's always on to, yes. Sorry, is it always on to? Sorry.
In terms of wall, but then also stabilization.
Yeah, I think there is some osteoporosis too that's supposed to be. So maybe, I'm sorry, let me take this back. In some situations, when you have an extra osteoporosis too, I think it's not to be onto this. In general,
And can a fiber be infinite?
well, yes, I think that's what Ruberman's example is.
Oh, it's already infinite.
There's an infinitely generated subgroup that the one has is just infinite.
Questions? Okay, if not, let's thank Slava again. We'll resume.